All right. Awesome. Hey, everyone. My name is Fraser Kane. I'm the publisher of Universe Today, and this is your weekly space hangout for Friday, May 30th, 2014. Man, when I say these words, it just sounds like I'm living in the future, 2014. So joining me this week, we've got Brian Coberline,
Hi.
and we've got Morgan Renberg. Hey, Morgan.
Howdy, Fraser.
And this week we are going to be talking about, of course, the new Dragon capsule, the maybe, maybe not, probably not gamma ray burst in M31 Andromeda. We're going to be talking about our black holes donuts, an update on the Bicep 2 results, robots repairing robots, an asteroid maybe going to smash into Jupiter in the future, and could there may be life on a Mars volcano? And anything else that strikes our fancy. So you can get involved. You can communicate with us. You can use the Q&A app, which is a cool little sidebar thingy in the Hangout where you're watching this. So wherever you're watching this on YouTube, just click that Fraser is interacting with the audience. Click that. It'll bring open another version of the Hangout. You'll see the little sidebar there, and a bunch of people are already posting questions and comments. And so as we do the show, I'll look through those. If you have some questions for the guests, we'll talk about them. All right, so let's go to the big news, which was last night, which was the announcement of the new Dragon capsule. Morgan, what's the scoop?
The scoop. So this is the second take, basically, on SpaceX's transportation system in space. We have the Falcon 9 rocket that launches cargo off of the Earth into space. But you got to put that cargo somewhere. And for the last couple of years, they've been putting it in the Dragon V1 capsule. And this is what is docked 4 times now at the ISS to deliver cargo and return experiments and trash and things from space. But now we want to have a new kind of cargo, and that kind of cargo is people. And to carry people, you need not only seats, but a lot of other safety equipment and technology to make the trip comfortable and safe.
Like, are they going to expect air?
And they need air and water and food and all of this kind of squishy people stuff that that boxes don't need. And so rather than just cram that into the existing Dragon, SpaceX went back and sort of reimagined the capsule. And I have a picture of it that I can share here. It looks a lot like the teaser. It looked a lot like the original the original Dragon capsule. But if you go inside, instead of a lot of places to strap down cargo, you have 7 seats that can carry astronauts. And instead of a bunch of control panels and things like you might see in a Soyuz spacecraft, you see 4 giant touchscreens. And these touchscreens, in combination with a few buttons and joysticks, allow the astronauts to completely control the capsule. But kind of the irony here is that with all this cool new control technology, they're going to need even less of it than ever, because now the Dragon capsule can dock completely autonomously with the International Space Station. It used to be that they'd fly up close to the ISS and wait for an astronaut on board to grab them with the Canadarm and basically push them into the airlock. And now the spacecraft can dock completely on its own with the space station, made up with the airlock, and allow the crew to transfer over.
But the Russians have been using that automated docking system for years, right?
Right.
They've got
That's
progress. Correct. Yeah. So that means clearly this is not. It's
right.
not rocket science.
The cool stuff, the sort of sci-fi aspect of it, is on the return. So currently with the Soyuz or the Dragon, these things detach from the space station, they fall back towards Earth. Their heat shields slow them down, they pop some parachutes, and they splash down into the ocean. And that works pretty well. It's relatively foolproof, but it means that you have to have kind of this small armada of ships go out and pick up your capsule. And so SpaceX is building off of their experience with developing the Grasshopper to make the Dragon capsule land using rockets anywhere on Earth. And Elon Musk, the CEO of SpaceX, said the goal is to have the Dragon version 2 land anywhere a helicopter can land. And so they show it, coming down. The heat shield slows it down, and then a set of rockets fire, and these rockets control very precisely its descent, and it can basically land right back onto the same launch pad that it took off from.
Now, is it not using a parachute system as well?
Right. So if all works as intended, parachutes are never deployed. But they do have parachutes on board, and what they do is as they're coming into the atmosphere, they start testing the rockets. They just give them little fires to make sure that they all are working. And if they're not working, then they can deploy the parachutes and land in the ocean, just like version 1. But that's only intended to be used as a backup system, and in fact, up to 2 of the jets on the Dragon version 2 can fail, and it can still land under its own rocket power.
That seems amazing to me, that it can do that. I mean, it's one of these things, right, that you, in the olden days, in the Apollo era, whatever, you're thinking about the fuel, and so you're having to lift that fuel up to space, mm-hmm. and then bring that fuel back down so that you can do your deceleration. But I guess one of the possibilities is you send the fuel up on a separate launch, you have it sitting in a fuel depot on the International Space Station, launch the Dragon on a lower weight, and then it refuels while it's on the space station, and then it can handle this. You're not necessarily having to carry the people and the fuel for that return voyage. I'm not sure the actual details and specifics.
Yeah, according to SpaceX, the fuel will be carried on board, and the rockets on the version 2 are far more powerful, about 160 times more powerful than the ones on version 1, and that's what enables this capability. But of course, we should include the caveat that this thing has yet to fly in space, and in the next 2 years they'll be testing these landing capabilities before they ever put people into it to make sure that everything operates as expected.
Like, I don't know, it feels to me like this is magic. Like, why has this kind of technology not been deployed before? I mean, at the end of the day, I mean, you've got rockets, they're firing out thrust. Someone should have been able to do the math and make this kind of technology platform work. I mean, I think to have your capsule come back to its location is exactly what you want. It's, then you don't have to move it, you don't have to chase it, you just have it land, eventually, have it land on top of another rocket, and you're ready to go with another launch. So, I mean,
the spacecraft industry is an exceptionally conservative one, and the goal is always reliability and safety. And so, once something works, whether that's bouncing lander on Mars or parachuting a capsule into the ocean, we're really reticent to change that because we know it works, we know it's reliable, and we know it's safe. And so in some ways it almost takes a new entrant into the field with new ideas to say, hey, we're going to try something different. And once they prove that it works and that it's reliable and that it's safe, you can imagine that we'll be switching over to this kind of technique.
Yeah, I mean, I say it jokingly, but if you can land with pinpoint accuracy somewhere on the landing pad, you could just as easily land on some kind of funnel that will bring it back down to the top of the next rocket. Like, these are the kinds of ideas that Elon Musk just says, why not? Why can't we do this? Why is this too complicated? You're fired.
You have to watch last night's press conference to see the sort of Silicon Valley influence on SpaceX. If there's, it's difficult to know whether SpaceX's rockets and capsules are actually substantially technologically better than those by Boeing or Lockheed or Sierra Nevada, etc. But what they've figured out is the PR game. They have us hook, line, and sinker in the press, and that's something I think that was well learned in Silicon Valley. Of course, Elon Musk came from PayPal, and so I think that they figured out how to engage the public and generate that excitement that in the past maybe wasn't so easy to generate, and that's only going to help the whole industry.
Yeah, and we've mentioned this in the last few shows that this problem, this breakdown of relations between the United States and the Russians is just a massive opportunity for SpaceX to jump in here with a human-rated launch, capsule, something that can fulfill this goal of getting humans up to the International Space Station and eventually to some of the other longer-term plans, to asteroids, whatever. And that although SpaceX, had a certain timeline, and NASA, I'm sure, said, here's how long you've got before we will want to buy these capsules from you. You just know that Elon Musk is in there with a whip going, faster, faster, come on, let's get this ready, because you know the Americans are going to get frustrated with having to buy this technology from the Russians, or the Russians are going to sable rattle, and they're not going to be able to deploy, a Soyuz, and then how are you going to get up to the space station? So this is a tremendous opportunity, and it sounds like, again, you're exactly right. He just did this gigantic press show and took everyone's breath away. But I mean, I think they have the stake to go along with the sizzle. I mean, they have launched
I
these
wasn't trying to
capsules.
suggest.
Yeah, no, they've got these rockets. We watched them landing on their landing pads. So I think this is all. It's the perfect match, and good on SpaceX.
All he needs is the metal exosuit, and he's done.
Yeah, he should just like pick up some astronauts in his exosuit and fly them up to the space station, and then also protect us from aliens.
Yeah.
Awesome. All right. Well, let's move on. Okay, so Brian, the other big story was, and we all sort of freaked out about this about 2 days ago, which was, oh my God, gamma ray burst went off in the Andromeda galaxy, a once-in-a-million-year event in our lifetime. Jump up and down. What happened and why did it not happen?
Okay. Well, first of all, a gamma ray burst is a high-energy burst of gamma rays. It's one of the things that we've seen from distant galaxies. We haven't seen it close up. And the Andromeda galaxy, being 2 million light years away, is actually close in astronomical terms. So we've been looking for this type of event. And it would be a very big deal because it would give us a very good view of what these gamma ray bursts actually are. So what happened is you've got the SWIFT telescope that's looking for gamma ray bursts. And it's got a couple of ways it does this. And one of this is it has kind of a wide field telescope. It's called the BAT. And what it's initially looking for is just a high energy burst of something. So it's basically kind of setting a wide net and saying, if there's anything that we detect, check it out, see if it rises to a possible candidate, and then try and see what it is. So what happened was the BAT detected this high energy burst. And at the time that it detected a high energy burst, the X-ray telescope was also pointed in the same direction, so they overlapped a little bit. And it also detected X-rays. Well, an X-ray afterglow is kind of a thing that could be a gamma ray burst. So gamma ray bursts can have X-ray afterglows. So it detected a burst of energy, it detected X-rays, and so it triggered. And it said, hey, we've got a possible candidate here. Well, this went through the astronomy community that looks at this types of thing, and of course they tweeted about it and everything else. When the initial data came through, because of various problems, the higher resolution data couldn't be analyzed first. So we had this low resolution data. That can happen if you have a large burst of energy that kind of washes out the high res sensor. So you start getting excited about this because here it is. It looks like the other one could be flooded. That's exactly what you would expect if it is in Andromeda. This is in the right direction of Andromeda. We could very well have a gamma ray burst. As you started analyzing the data, it became clear that this was an X-ray. It's from a known X-ray source. It wasn't a gamma ray burst. It's nothing atypical. Basically, it was a series of events leading to a trigger, leading to not being able to have the high resolution data to eliminate it as a possibility early, and so you have a whole bunch of excitement. So this can happen sometimes. We'd rather, particularly for a close one, we'd rather err on the side of caution than not. And in fact, SWIFT is actually designed, in general, I think it's got a 6.5 sigma cutoff in order to trigger for a general gamma ray burst, but about a 3 or a 3.5 sigma, so much lower standard for anything in a local galaxy. So that's part of the reason why it triggered too.
I really hope that this doesn't cause people to I don't know, pull back on the way they released the data to the internet, because I think this was the perfect response. This was exactly what you want. The spacecraft detected the burst, detected a flood of X-ray. The information was released out to the internet. People were able to jump on board and were able to start trying to image Andromeda and try and catch the afterglow and maybe even find the progenitor, and then false alarm. But I mean, it's the same thing with like fire alarms. I mean, that's what that whole thing means, right? You pull the fire alarm, the fire department shows up no matter what, and it was a false alarm. Well, better to have the occasional false alarm, but when the real disaster occurs, you're there and the response is there, and I think it's exactly the same. So I really hope, if there's anyone out there kind of saying, well, we got to change the way information is released to the public and whatever, stop it. This is right.
Well, and one of the things that's interesting to see is that if you look at it on Twitter, I think the tag they used was GRB14. I'd have to look up the exact tag, but there's a tag in which
31 or something.
Yeah, M31. Yeah, GRB M31. So if you look up the tag GRB M31, you can actually go through the timeline and you can see the initial first tweets by some astronomers. You can see how they are very clear in both their excitement but also their cautious level. Possible candidate, possible this, and then you start seeing information getting exchanged very quickly back and forth between different observations.
Yeah.
And that's what's really cool, is that you see, hey, everybody, pay attention here, and then you start seeing this rapid-fire exchange of information between different observations and different data very quickly.
Yeah, and astronomers in the right regions were going out and they were turning their telescopes towards M31, and I'm not seeing anything here, so it was perfect.
Yeah, it was exactly it, and it's fascinating to see that in a span of about 24 hours or 72 hours, we went from trigger to event to spreading information to confirming what it was.
And this is exactly how science has to work. This is absolutely perfect, and I'm really glad that astronomy anyway can provide these kinds of examples to show other scientists how you can collaborate, you can work really quickly, you can get this data out there, and you can confirm it or deny it as quickly as you need to. And I think it was exactly perfect. So I would love more of that information flowing out there in every field of science. I think it's great. I was so excited, even when it didn't happen, just to watch the thing unfold, to be a part of it was wonderful.
Yeah.
It felt a bit like the Chelyabinsk meteorite.
I think that's another good example of something in real time that became very exciting.
Yeah. But would have been amazing to have a gamma ray burst in M31. So.
Oh yeah.
That's sad. All right, Morgan, you've got a story this week about robots repairing robots, and I have no idea what you're talking about, so please tell me.
All right, so this is taking place on the International Space Station. And the ISS, as we have learned all too frequently, has machines, technology, equipment all over it, and that stuff breaks, just like it breaks in our house. Of course, when it breaks outside, you can't just call, your local handyman to come fix it. You got to send astronauts out there in their spacesuits to do a spacewalk, and that's just a huge pain. And it's also very dangerous for the astronauts. It takes weeks or sometimes even months to plan these spacewalks. It can take, 6, 8, 10 hours to execute one, time in which everyone on the space station is completely focused on the execution of that spacewalk, and you risk your astronauts. As we've seen in the last year or two, spacesuits don't always work as intended. Spacewalks don't always come out flawlessly. And so NASA would like to reduce, I think they'd like to eliminate, but they're going to work to reduce the number of spacewalks necessary. And one part of that was the commissioning of a robotic repairman called Dexter. And Dexter is built by the Canadian Space Agency. And his job, or its job, I guess, is to move around the outside of the space station and repair equipment on the outside. And I got a picture of it here. So in this little circle here, you can see Dexter mounted onto one of the modules of the space station. And so if a solar panel breaks or you need to replace an imager or a computer or something, you can use Dexter to do it rather than using an astronaut. And that's been happening on and off now for the last few years. But for the first time ever in this last week, Dexter was actually repairing not just a instrument on the International Space Station, but a whole separate robot. And you can see that right to the right side of your image, you see the Canadarm2. The Canadarm is used to manipulate things outside of the station, like, for example, grabbing the Dragon capsule and docking it, or moving heavy equipment around for astronauts to use. And it has cameras on board for seeing what it's looking at. And one of those cameras was starting to degrade. So rather than send an astronaut out there, NASA commanded Dexter to replace that camera with a spare. And all that the human astronauts needed to do was take that camera off of a shelf inside the ISS and put it in the airlock. Dexter was then able to go open the airlock, grab that camera, maneuver over to the Canadarm, remove the old camera, mount the new camera in place. And this saved a lot of time for the astronauts. It saved a lot of money in terms of the planning and design of this spacewalk, and it resulted in success without needing to risk the astronauts.
Yeah, that's the future. I mean, it's surprising that it took this long to have this stuff being done by robots.
Yeah, you have to design your equipment in careful ways for robots to be able to use them. You have to have robot-friendly screws and bolts and nuts, and you can't use some materials that we use commonly in space. For example, that kind of foil wrapping that you see on practically anything in space, which is called a thermal blanket. Robots have difficulty with that because it doesn't behave in an expectable way. You grab it and it's going to kind of deform. And so we've had to sort of develop an understanding of what robots can and can't do, and then build components of the space station that are addressable by those robots. But now it's starting to take effect, and we're able to reduce and hopefully one day eliminate the need for people to venture outside of spacecraft and space stations to do this kind of work.
Right on. I had another rant I was going to queue up, but I think I'll save it. So our friend Roshan Bukhari is trying to watch the live video, can't, but has a question for the panel. So I thought I would just throw this in here. Why is the moon in the habitable zone, but not a habitable body? So I guess he was a planetary scientist. Morgan, I'll throw this one at you.
All right. So there's a number of reasons. One of the things that we think we need for to be habitable is an atmosphere. An atmosphere provides pressure that can allow things like liquid water to exist on the surface. And what you need for an atmosphere is a body massive enough to hold that atmosphere in. And so the Earth is massive enough that molecules like oxygen and nitrogen, carbon dioxide, are heavy enough that our gravity holds them in, and they make up our atmosphere. There's not a lot of hydrogen or helium in our atmosphere because those elements are too light and they just escape away to space. We had them in our atmosphere early on, billions of years ago, but very quickly they bled off into space. If you look at the moon, it turns out that even heavy, what we call heavy gases like oxygen, nitrogen, carbon dioxide, are still too light to be held by the moon, and so they simply escape away. And this process is exacerbated by the fact that the moon doesn't have a magnetic field. And magnetic fields protect atmospheres and surfaces from the effects of the solar wind. And if you want to see kind of that in action, all you have to do is look at the difference between the Earth and Mars. The Earth and Mars are relatively similar in size. Mars is certainly heavy enough to hold on to things like carbon dioxide, yet its atmosphere is at most about 1% of the Earth's. And a lot of that's attributed to the fact that it doesn't have a magnetic field, and so the solar wind just kind of smacked into the atmosphere of Mars over billions of years and just blew it away.
There you go. I hope that helps get you through not being able to watch the live video, Roshan. We're thinking about you. Okay, so let's move on to, I guess, another update on Bicep 2. Last week, Brian, you were hopeful that Bicep 2 would be confirmed, but there was a few cracks in the data. Where do we stand now?
More people are whacking on this paper, and there's getting to be more cracks. basically, it's still going through the peer review process. So, this is how we do science. Somebody comes up with a paper, and then we whack on it until it succeeds or fails. Nature reported there were a couple of new papers, these are still preprints, that are analyzing the BICEP2 data, comparing it to what's called the foreground data. So basically, BICEP2 is looking at data from the cosmic microwave background, which is the most distant thing that we can see. Everything else is in front of it. So it's kind of like trying to look at a distant wall through a crowd of people. And you have to be able to account for all of the distortions, blockages, other sources of microwave radiation that could disrupt what you're trying to look at. BICEP2 thought they had accounted for all the major interferences, all the major foreground effects. And these new papers are looking at it that they may not have. Basically, if you take some of the Planck data and if you look at the foreground effects of that, it's stronger than what BICEP2 had accounted for. Now, these new papers are arguing that they're strong enough to kind of wash out the BICEP2 results. So their conclusion is that BICEP2 can neither confirm nor deny the existence of this inflationary period. The BICEP2 team is disputing it. They have not retracted the paper. They are still going through with peer review. So now we're getting more stuff of foreground effects. They may be more of a problem than BICEP2 had anticipated. Where this goes is still through the peer review process.
And even if, I guess, all of the foreground effects get accounted for, that doesn't mean that there might not be other foreground effects that people just haven't thought of yet.
Right. Well, this is the foreground effects are probably the #1 issue. Gathering the data is, I'll say, straightforward, but that's not to minimize how hard it actually is. Analyzing data is tedious and careful. Foreground effects are always your Achilles heel. You have to be able to account for it in the right way. And so this is where having multiple data from multiple sources is always going to be a good thing. When Planck releases more of their data, BICEP2 releases data, we're going to have a better comparison of this.
Right, but I'm just saying, like, you might say, oh, maybe the foreground effect could be from interstellar gas in the in the environment, and then someone could go, yeah, we've accounted for that, and it's not it. And then later on, oh no, wait, it could be magnetic fields from the galaxy. Oh, or it could be interactions with dark matter, or whatever. The point is that there's an almost limitless number of possible foreground effects. So even if you deny one of them, there could be another one that people could not even realize. Oh no, it's the what's it, the aether, right? Like, it could be something else. So that's a tough job, right? You need to come at that data from a completely different way, as you're saying, with the Planck data or whatever, and confirm it separately in another way that you can start to build up that.
And this is where multi-spectrum data becomes useful. When you look at them on different spectra, then you can actually, it's better, it's easier for you to pull out the foreground effects if you look at different spectra, because the cosmic microwave background has a very specific distribution.
So place your bets.
I think BICEP2 is dancing on the edge. I think it's capable of determining this inflationary polarization. I don't know if it does or not.
But isn't this in line with some of the stuff we reported on last year about how maybe there isn't a lot of evidence for inflation, and in fact some of it's starting to fall away? That as if I recall, I think Dr. Francis was talking about this last year, that some of the evidence is getting a lot stronger that inflation didn't happen, that there isn't the evidence for it. And so to then come back and go, no, look, we found it, it's right there, and now you're like, well, wait a minute, maybe not.
This is an interesting
going away.
We have some level of contradictory evidence, and it's exciting in one way because it means that we're honing down on something important, but it's frustrating on the other level because you get this kind of back and forth and back and forth. And one of the things to keep in mind is this is specifically about a detection of the inflationary period of the early universe. This has nothing to do with the standard model of an expanding Big Bang universe. That's largely settled. We're looking at minor details of an early period within that Big Bang model. And so even if this gets thrown out, it doesn't mean that we're in a stationary universe. It doesn't mean the Big Bang never happened. It means that it happened in a different way.
Does any of this help us get at whether or not the universe is finite or infinite?
Well, the inflation period, I mean, if there's no inflation, then we need a mechanism that can account for the homogeneity of temperature in the background. And right now, inflation looks like the answer. You know, we don't really have a good solution. And we may find out that they actually are a good solution, but right now, inflation is the one. So if you have inflation, then it is very likely that we have an infinite universe, that we have multiple universes. The Bicep 2 is looking at a type of inflation where you would have eternal inflation, where you would have different regions that are always inflating at different times, and that's kind of the multiverse idea. If all of that goes away, we have a radically different view of what our universe is like. I mean, this is, if we actually can show that there is no inflation, if we see actually a negative observation, which is different from a lack of observation, if we actually show no, there is no signature of inflation, that will radically change our understanding of the early universe. Right now, we're not there. Right now, we're still struggling with, can we even detect it?
All right. Stay tuned.
Stay tuned.
Okay, cool. So a couple more stories. Morgan, apparently an asteroid is eventually going to whack into Jupiter.
Maybe.
Maybe.
So this was an asteroid that we discovered earlier this year, and it recently passed relatively close to the Earth, about a fifth the distance between the Earth and the Sun. So that's a long way away if you're an asteroid hunter. This is the sort of thing that we don't worry about at all. But, you know, it's interesting enough to note. And so somebody looked forward and found that, hey, in about 7 years, this is going to get pretty close to Jupiter. When I say pretty close, I again mean a pretty long way away, about 155 million kilometers away, which puts it in the Jupiter system. There are moons of Jupiter that are farther out than 155 million kilometers, but it doesn't put it very close to Jupiter. And in fact, the uncertainty in where it will be 7 years from now is about 5 times that 150 million kilometer distance. So we really don't have a great idea. And this is because we only observed this asteroid for 5 days nearby when it passed to the Earth. And so you can imagine kind of taking 5 dots on a graph and putting a line through them. You can put several different lines that will go close to those 5 dots. And you know, for the next 3 months, all of those lines will be in roughly the same place. But if you were to go way out along that line, even a tiny little variation in that line is going to have a huge effect 7 years down the road. And that's the problem that we have in thinking about whether or not asteroids will hit the Earth in 100 years, or in this case, whether this asteroid will hit Jupiter in 7 years. And so right now, the best estimate is it has about a 1% chance of hitting Jupiter in 2022.
Forget about it.
And so there's an easy way to solve this, which is just to wait a little while and look at it again. Because it only takes a couple of points a little bit down the road to vastly constrain the number of different lines you can draw through those dots. And this is what we do on the Earth. If this asteroid was coming towards the Earth and had a 1% chance of hitting the Earth, we'd call it a virtual impactor. And virtual impactors mean there's at least one possible route the asteroid could take that would come within striking distance of the Earth. We've seen hundreds, maybe thousands of virtual impactors over the last 10 or 20 years. Not one of them has ever actually turned out to hit the Earth. Usually we do one more observation a few months down the line, and we're able to 100% rule out the chance of it hitting the Earth. And I expect that's probably what will happen again here with Jupiter. Which is too bad, because if we did see an asteroid like this hit Jupiter, it'd be pretty interesting. You know, this is going to be a couple hundred meters across asteroid, and if we watched it with something like the Hubble Space Telescope, we would see it enter the atmosphere of Jupiter and break apart. And the speed and size with which it breaks apart tells us something about the composition of the atmosphere of Jupiter, the density, the molecular composition, the pressure. And surprisingly, maybe, these are things we don't understand very well at all. We learned a little bit back in the 90s with Galileo. We learned a little bit when Comet Shoemaker-Levy 9 impacted Jupiter, also back in, I think, 1994. And that's about all we know. We have an idea of how a few bits of the outer layers of Jupiter work, but we don't have a lot. And so something like this would be a big boon, especially if we knew it was coming 7 years from now. We could really put in effort to get observations in place to study it. But with only a 1% chance of hitting Jupiter, it's unlikely that much effort will be expended to do that.
Right.
Yeah. I mean, we sure learned a lot with Shoemaker-Levy 9. I mean, that was one of those lucky breaks. I mean,
absolutely.
Once in a, I don't know, 1,000-year comet cracking up and falling into Jupiter like that. I mean, it's amazing that we got a chance to see that.
Yeah. But even if it misses, it's still kind of useful because this kind of close approach to Jupiter helps us understand the interaction of Jupiter with asteroids and how you can get deflection like that from close approaches.
Right. One of the big unsolved questions right now is Jupiter, did it protect us from asteroid strikes, or did it redirect asteroids towards the Earth and actually cause us more devastation? And I know that's still a bit of an unsolved question.
Right. Yeah.
Okay, cool. So I think last story we've got here is, could there have been life on a volcano on Mars?
Yeah, this is another maybe.
Maybe.
So the volcano that we're talking about is called Arsia Mons, and it's the third largest volcano on Mars, which makes it one of the largest volcanoes in the solar system. And what astronomers found using observations from the Mars Reconnaissance Orbiter, which is our highest resolution camera orbiting Mars, is an interesting piece of terrain, and I have a picture of it here, where volcanic flows, so this would be like lava flows, seem to come nearby to regions that might have had glaciers. So what we're looking at here is a topographical map of a piece of Mars. This is Arsia Mons at the top. And then we have this kind of zoom box, and we see these long straight lines, and we see all these little pits. And these long straight lines are indicative of volcanic activity. You can imagine seeing pictures of lava running down the sides of volcanoes in Hawaii, for example. These pits are indicative of glaciers. We see these, for example, in the Canadian Shield. And with their close proximity here, what we have is the possible situation where lava flowing by these glaciers melted some of the water in those glaciers. And so we have water, we have energy, we have nutrients in the form of volcanic particles, ash, dust, soot are all good sources for microbes. This is a place that if you were a microbe and you happened to be there, you might be pretty happy. The problem is that this situation probably only lasted for a few hundred or maybe 1,000 years. And that's not long when you're talking about life. And so there's almost no chance that life developed in an area like this. But had life already existed on Mars elsewhere and kind of gotten blown in the wind and landed in this area near Arsia Mons, this would be a pretty happy place for you to live. But that's a big if. You know, for that to be the case, there must have been better conditions elsewhere on Mars for life to arise. And at this point, we just don't see the evidence supporting that.
Right. But I mean, it might be a good place to send a rover.
Yeah, it'd be certainly a geologically interesting place where you have the interactions between two of the major forces that shape planets, which is volcanism and water or glacier activity. And so I think you'd find a lot of fascinating geology in this region, which of course sometimes makes it a bad place to send a rover because fascinating geology often means difficult to drive on.
Yeah. Well, I got a bunch of questions here from some of the viewers, so why don't we get through some of those and we'll sort of move on. So first, about the Spacex capsule, Nancy Graziano wonders, is there a crew escape jettison mechanism included in this, similar to what NASA manned rockets had in the past?
They didn't talk about that yesterday, but I believe that that's in the specification for all of the manned crewed systems that NASA's funding or developing. And just to be clear, this isn't like ejecting in space. This is ejecting the capsule off of the rocket either prior to launch or shortly after launch. And this is when most rockets fail, is either on the launch pad or within a few minutes of leaving the launch pad. And so the goal there is to blast the capsule away from basically this giant exploding bomb. Once you're in space and you're stuck. There's no getting out at that point. You got to come back through the capsule. But as far as I'm aware, NASA's mandated that for all their systems after lessons learned, of course, in the space shuttle era.
But you would think that if this thing is capable of landing back on Earth and it's got fuel and rockets, it's got more than enough capacity to be able to boost itself off the rocket and probably like fly off and circle around the rocket a couple of times and land back nice and safely on the launch pad. I mean,
usually how these things work is it's a separate rocket that's pointed perpendicular to the big rocket because you want to get away, and this thing's exploding like a bomb, you want to get away as quickly as possible. And the fastest way to get away is to go sideways, not try to fight gravity, and not try to fight the momentum of the rocket, which is already going up, but to blast sideways as fast as possible, put distance between you and this just exploding rocket.
Right, and then it's going to have this rocket system to control its descent again. So I'm sure it's something that they've thought through, and as you said, NASA has made this a requirement.
Right, safety is the #1 priority
I know,
in all of these systems.
On some of them, right, there's like another rocket system that sits on top that's got boosters, right, and it can kind of pull the capsule off the top. So it might be that there's more hardware that just we're not seeing, that a lot of this is maybe, as the launch is starting to happen, this stuff is discarded and it's separate from the capsule itself.
These are the tests that we're going to see over the next 2 years, because you can bet before they put people in this, they're going to test the launch escape system. And knowing SpaceX, we'll see a video with some cowboy music behind it, showing this in action.
Yeah. Let's see if there's anything else. Well, Elad Avron wants to know, how will it navigate within the atmosphere? Are the rockets that precise?
I think that the main trajectory is going to be set prior to entering the Earth's atmosphere. The angle and the velocity with which you enter the atmosphere will, to a pretty good approximation, put you on your final destination. And this is the same mechanism the space shuttle used. The space shuttle wasn't firing rockets once it was entering Earth orbit, or entering the Earth's atmosphere, excuse me. You put yourself on the right trajectory to get relatively close, and then you fine-tune it. In the space shuttle's case, they had flaps and wings and things to adjust and glide like a plane, and in this case, they'll be using the rockets to sort of nudge themselves into the right direction.
Right, and so you can kind of, I guess it's all just about whether you want to land softly or you want to land hard. That's, you're going to land at roughly the same spot. It's really just about velocity.
Yes.
And John Gallant says, what about the 3D printed Dracos? So they did a test of the Super Draco engine just like 2 days ago or yesterday, and we had a video of that on Universe Today. And I got a chance to tour SpaceX, and maybe I've told you guys this story before, but they have the ability to 3D print titanium. And so one of the SpaceX workers gave me this block of titanium to check it out, and it looks like a block of titanium. He said, hold it up against the light. So you hold it up, and you can see the light coming through the titanium. And so the resolution of this titanium printer is unbelievable. And so it can print, they just did it as like check this out, that it can have these really microscopic holes all the way through the titanium. It has that high resolution, and so they're able to print off these engine parts, motorized parts, whatever they want. And so I guess with these Draco engines, a lot of the chunks of them are printed in titanium.
Right. Musk confirmed last night that they were in fact printing the parts for the Super Dracos on the Dragon V2.
Yeah.
So that must have progressed to the point where they're happy with the quality.
Yeah. Amazing, just this kind of technology, Like, again, it's just like just these ideas that are all just making their way into the process is just great. Let's see. Okay, so let's move on to some of the other. We'll talk about the bicep one. Sorry. Andrew Planet wants to know, could the inflation of this universe be an aftermath diffusion of a relativistic burst of energy condensing and accelerating towards the gravitational field of another universe? Brian.
Probably not.
Probably. I guess.
There are ideas of our universe coming from other universes, such as from the internal regions of black holes and other universes. That's an idea that's been looked at for a long time. It's hard to gather the evidence for it, but it's certainly within the realm of possibility. Knowing what we know about the densities within black holes, knowing what we know about the early universe, there are similarities. There are ways to connect them. Whether that happens to be the case or whether it happens to be something else, that's still based on the evidence. We just don't have enough evidence. But there are these ideas of our universe being a child of another universe that's out there and have been studied in detail.
And Nancy Graziano asks, even if the current results of Bicep 2 ultimately are shot down, do you think the team is on the right approach with their method for detecting E-mode polarization and proving inflation? So, I mean, if it turns, I guess the question is, like, if we don't crack holes in this research and it turns out that yes, indeed, is E-mode polarization in the cosmic microwave background radiation, is this a slam dunk pretty much for inflation? I guess Nobel Prize material, right?
This is a Nobel Prize level work.
Yeah.
I mean, you have to be able to detect it. You have to get to the point where you can distinguish between different types of inflation. This is a very difficult experiment, but it has the potential of being a very powerful experiment. It's one of those things where we could not have done this 5 or 10 years ago. It requires massive amounts of data, massive amounts of statistical analysis. So it requires both sensitive detectors and computing power. And as we get better detectors, as we get more computing power, we're going to be able to fine-tune this. I think this is the right track, and that this is a very viable way to determine inflation. This could revolutionize in the same way that understanding supernova measurements to look at an inflationary universe, this could be the same type of thing where we can now get direct evidence from the earliest moments of the universe. We can see beyond the cosmic microwave background.
So it's worth doing right.
It's worth doing right. And that's part of the reason why there's so much criticism. It's because it's such a huge deal.
Yeah. Nancy Graziano would also like to know if Dexter has any extra replacement reaction wheels with him. I don't think he needs them.
Yeah, I don't know. Can toss one over to Kepler.
Yeah, if he could just pick one up and just throw it and see if Kepler could catch it.
Where's Clooney where we need him?
Okay, great. Well, let's wrap things up. So before we do, though, we want to give lots of information about my participants here. So Brian Koberlein, where can people find out more about you and appreciate the wide variety of things that you do for science?
Well, you can find me on my website, one universe at a time. It's briankoberlein.com. You can find me on Twitter at Brian Koberlein. And coming Monday, some of you might remember Prove Your World Project. Coming Monday, a new series of videos comes out on Prove Your World.
That's awesome. So you've kept going even still keeping them coming out. Do you see Reading Rainbow earned $2 million on Kickstarter?
I think 2.7 million.
Yeah, in like a day.
It's amazing.
Yeah, so the hunger is there for that kind of information. So keep it going, man. Morgan, where do we find out more?
Yeah, well, first off, I'll be taking questions that we didn't get a chance to answer today over at the Google Plus Space community. Just head to plus.google.com, click on Communities, find Space, and join us there and ask me anything you'd like. You can follow me on Twitter at Morgan Renberg, and you can find my writings at Cosmic Chatter
Fantastic. And of course, I am the publisher of Universe Today. You can listen to me on Astronomy Cast, and you can watch on this YouTube. We've got a whole pile of videos coming shortly, some of them penned by Brian Coberline, in fact. So they will be coming out. I think we got our next one on Monday, and we've got like 16 of them in the can, so they're going to come out regularly from this point on. So thanks everyone for watching. Thanks to the good folks for joining me today, and we will see you all next week.